Hello, welcome to my talk on the flight dynamics of boomerang, where I will be discussing the impact of joint angle. My name is Ethan Foss. I'm a fourth year undergraduate student at the University of California, San Diego, studying mechanical engineering. The research that I will be presenting today is a joint effort of undergraduate students in the fields of mechanical, aerospace, and electrical engineering, supervised by Professor Prasad Gudam, professor at UCSD with an avid interest in boomerangs. To start, I will give an introduction to boomerangs, their history, and the basic physics behind them. Boomerangs have a rich history of use in hunting dating back tens of thousands of years. Non-returning boomerangs, which are used primarily for hunting purposes, were used on every continent across the Earth and have been found in Egypt, Europe, India, and Australia. Returning boomerangs were found only in Australia and have been suggested to have been used to hunt birds. More likely, though, they were used as toys. In this video, you can see a typical throw of a boomerang thrown by me. As you can see, the boomerang is thrown nearly vertically with both rotational and translational speed. After making a loop, it returns almost horizontal. This is a particularly good throw since I didn't have to move at all to catch it. So how do these mysterious flying objects work? Boomerang blades are made up of airfoils, which generate lift when flying through the air. Due to the combination of the rotational and translational velocity, leading edge blades encounter greater lift than the trailing edge blades. The asymmetric lift on the boomerang generates a rolling moment, causing the boomerang to pitch in a circular trajectory. Prior research on boomerangs dates back to the 1970s, starting with Felix Hess. His work, along with work done by John Vosburgh in 2012, greatly expanded the understanding of boomerang aerodynamics. However, their work, along with the work that our research group has been performing, mainly focused on tri-bladers boomerangs due to the simplicity of the analysis. Research by Akira Azuma and Goro Beppu is some of the most comprehensive work done with regards to elbow boomerangs, though their research does not include any field trial data and fails to predict the trends that we see on the field with increasing joint angles. With that summary of boomerangs, we can now talk about some of the research that our group has been working on for the previous years. First, we will talk about the field trials and data collection that we performed. To facilitate the study of boomerangs, we moved towards manufacturing boomerangs with a 3D printer. This allowed us to easily customize our boomerangs to our needs, such as adding compartments for the electronics and modifying the boomerang to fly within our measurement range. The 3D printer also ensured consistency, both in terms of geometry and mass. Moreover, we could easily and quickly manufacture the boomerangs ourselves. To measure the position of the boomerangs in time, we took advantage of ultra-wideband technology, which can provide a position accuracy of less than 10 centimeters under dynamic conditions. Since our previous work, we have greatly decreased the size of the UWB tag by embedding it into a custom printed circuit board. As you can see that the second generation UWB tag embedded in the small arms of the elbow boomerang on the right is much smaller than the first generation UWB tag embedded into the center of the large tri-blader on the left. Using a network of 16 mesh network anchors, outlined in red on the leftmost video, we can triangulate the position of the boomerang in time, giving data for the boomerang trajectory. We collected data for boomerangs of varying joint angles in low wind conditions. We performed about 15 trials of each boomerang, choosing a representative trajectory for each based on which trial exhibited the most average behavior. Videos from the field trials also allowed us to estimate rotational rate data for the boomerang over its flight. Here on the right, you can see the results from the field trials for boomerangs of 60, 90, 105, and 120 degree joint angles. We can see that the joint angles of the boomerang increase, the trajectory becomes more elliptical and eventually fails to return at all. On the left, you can see the results from the aforementioned work on elbow boomerangs published in 2004 for boomerangs of 110, 120, and 130 degree joint angle. You can see that the flight trajectory simulations for large joint angle boomerangs fail to replicate the trajectories that we see in the field trials. Through analysis, we would like to produce a model for the boomerang that not only is able to replicate the trend that we see in the field trials, but can also describe why we see this phenomenon on the field. Now I will talk about some of the analysis that we performed in modeling the mass properties, aerodynamics, and simulating the boomerang trajectory. The moments of inertia of the boomerang change with joint angle. We assume a simplified geometry for both the derivations and for the experiments to simplify the analysis and reveal the trends of boomerang flight through analytical expressions. Using this geometry, we can derive analytical expressions for the center of mass and moment of inertia of the elbow boomerang. On the right, you can see a plot of how the normalized moments of inertia of the boomerang change with joint angle. With larger and smaller joint angles, the difference between Ix and Iy becomes larger, a property that is highly influential on the boomerang's flight. We can model the aerodynamics of our elbow boomerang using blade element theory. This is very similar to the work that has been performed on tri-blader boomerangs. However, elbow boomerangs do not rotate about the center of the boomerang, which complicates the derivations. Specifically, we would like to model the lift and drag on the boomerang, along with the rolling moment, pitching moment, and drag moment. Using blade element theory, we were able to derive integral expressions for these forces and moments as a function of the elbow boomerang joint angle. Here, we can see plots of lift and drag coefficients changing with boomerang joint angle at a range of rotational rates. The leftmost plot shows the lift, and the rightmost shows the drag. The topmost show the coefficients due to no angle of attack, and the bottommost show the coefficients due to angle of attack. We can see that these coefficients, apart from drag due to angle of attack, both increase with increasing joint angle and increase with increasing angular rate. Likewise, we can plot moment coefficients changing with boomerang joint angle at a range of rotational rates. The leftmost plot showed the rolling moment, the middle plot showed the pitching moment, and the rightmost plot showed the drag moment. Like before, the topmost show the coefficients due to no angle of attack, and the bottommost show the coefficients due to angle of attack. Again, we can see that these coefficients, apart from pitching moment due to angle of attack, both increase with increasing joint angle and increase with increasing angular rate. With the mass parameters and aerodynamics of the boomerang modeled, we can simulate boomerangs of different joint angles in 6 degrees of freedom and compare the simulation results to data taken from the field trials. On the right, you can see the results from these simulations and their corresponding field trials for 60, 90, 105, and 120 degree boomerangs. The simulations were able to predict well the trajectories of the 60 degree and 120 degree elbow boomerangs, which would suggest that the model is successful in predicting the trend associated with increasing joint angle. This promising result has not been captured in previous research. However, the simulation is not successful in replicating the trajectories of the intermediate angle boomerangs, as seen with the 90 and 105 degree boomerang. Clearly, to completely capture the full trend of the elbow boomerangs, further improvements to the model are necessary. We have some ideas for model improvements that we would like to tackle in future works. Specifically, since the airfoil model is linear, the model is inaccurate at high angles of attack. When the boomerang approaches stall, rolling moment and lift forces are over-approximated, whereas drag force and drag moments are under-approximated. Moreover, we believe damping effects to be an important aspect in boomerang flight that is not currently modeled. High amplitude rotations of the boomerang would incur counteracting damping moments. Lastly, we believe the aerodynamic derivation for pitching moment to be insufficient and posit that tangential flow acting on the blades of the boomerang would increase the pitching moment effect. In this work, we were able to collect trajectory data for 3D printed elbow boomerangs of numerous joint angles using UWB technology. Moreover, to explain the trend that we saw in field trials, we derived expressions for the aerodynamic forces and moments of elbow boomerangs. We were able to derive analytical expressions for the mass properties of the boomerang. Using these models, we simulated the trajectories of our boomerangs and compared them to the experimental results. Our model was able to predict the trend seen with joint angles of 60 and 120 degrees, but was unable to predict the trajectory seen for the intermediate angle boomerangs. Future work will study improvements to the model and close the gap between simulations and experiments. Thank you for listening to my talk. Though I am the one presenting, the work done would not have been possible without the help of my fellow undergraduate students who helped me gather measurements for our experiments and help lay the foundation for this research. I would also like to give a special thanks to Professor Gudon. Without his guidance and insight, this research would not have been possible.